Alright, hello. So we're going to continue our discussion of galvanic cells, and we've talked about cell potential, and now we're going to look at the dependence of cell potential on concentration. And so cell potential does depend on concentration, and so far we've assumed that we are under standard conditions, which means that all concentrations are at 1 molar. And so let's say we have this balanced redox reaction. So we have copper solid plus Ce4 plus, or ion, copper ion, and we've got a standard reduction of 1.36 volts. Well, what if one of our ion concentrations increases? And this happens to be one of our reactants. Well, if you think back to Le Chatelier's principle, the forward reaction will be favored because we're adding more reactants, which will then push the reactant toward the products. And so the forward reactant will be favored. And so this means that the driving force on the electrons will increase and the cell potential will increase. And then the opposite is also true. Let's say that we increased one of our product concentrations instead. This would favor the reverse reaction, which would decrease the driving force on electrons because electrons would be flowing the other direction or not flowing the forward direction, and this would decrease our cell potential. So let's look at an example. So for the cell reaction, 2 aluminum, 3 manganese ions, 2 aluminum ions, 3 manganese solid, the cell potential is 0.48 volts. We want to predict whether the potential of the cell would be larger or smaller than the standard reduction potential given these non-standard conditions. So for the first one, we are increasing our aluminum ion, so we are increasing I don't know what's going on with that. Okay, we're increasing a product, and our manganese ion is 1, and that's our standard. So if we increase the product, we are going to shift equilibrium this direction, so we're going to shift it left, which means it's going to decrease the cell potential. So E of the cell is going to be less than standard cell potential. Now let's look at our other one. Our aluminum ion is 1 molar. That's our standard concentration. And our manganese ion, which is a reactant, is larger. So now we're increasing a reactant. This is going to shift, according to Le Chatelier's principle, in the forward direction, so it's going to shift right, and this will increase our cell potential, meaning that our cell potential is going to be greater than our standard reduction cell potential. So it's very similar to Le Chatelier's principle and based on that. Okay, so due to dependence on concentration, we can construct galvanic cells that contain the same components on both sides, but they're at different concentrations, and this is called a concentration cell. But it'll work the same way because of that difference in concentration. It's still pushing the electrons one direction, and so this means that the difference in concentration is the only factor that's going to produce a cell potential. For these types of cells, the voltages are typically small, and electron flow goes from left to the right, and so that would mean that we would have the anode on the left side and the cathode on the right side. Okay, so let's look at one of these. So we're going to determine the direction of electron flow and designate the anode and cathode for the cell below. Okay, so if we take a look at what we have going on, here we have 0.2 liters of copper sulfate, and it's 1 molar. And here we also have 0.2 liters, so our volumes are the same, but our concentrations are very different. This concentration is much less, and so because it is much less, electron flow is going to go from the right to the left. So electron flow should go this direction. And this means that this is our anode, and this is our cathode, meaning things here are going to be oxidized and things on this side are going to be reduced. And so because it's being oxidized, it's losing electrons, so we are going from copper solid to copper the 2 plus ion plus 2 electrons. Okay, because what we're trying to do is increase the copper 2 plus over on the cathode side since the concentration is so much less. That's why the electron flow is going that direction. And so that's why this side is being oxidized, because we're taking from our copper electrode and making it into ions on the other side, which is pushing the electrons from right to left. On the reduction side, our ions are producing copper, which is then increasing the concentration on our electrode. Okay, when we have non-standard conditions, we can use what's called the Nernst equation. So that the dependence of cell potential on concentration results directly from the dependence of free energy on concentration. So this is where we're linking in equilibrium with concentration with our G, or our free energy. So the Nernst equation says that the cell potential is equal to the standard cell potential minus RT, so R being our gas constant, T is temperature, N representing the number of electrons transferred, F representing Faraday's constant, natural log of Q. Remember, Q is similar to K, but Q represents initial conditions, whereas K represents equilibrium conditions. And because not all of our conditions are standard, we're going to use Q. Well, if we take R and T and F, which are basically all constants, or if we assume that we're at 25 Celsius, so then temperature does become a constant, then we can come up with just a term for this instead of all these variables. And so at 25 Celsius, which would be room temperature, most of our galvanic cells would be at this condition, then the reduction potential for the cell is equal to the standard reduction potential minus our 0.0591 over N, that's just the result of all of these, times log of Q. And so we already talked about N representing the number of electrons that are transferred, and that's why when you have the two half reactions, you have to make sure that number of electrons transferred is equal on both sides. So we're going to use this to calculate the cell potential when the components are not in their standard states. So let's look at an example of that in a minute. Okay, so the potential from the Nernst equation is the maximum potential before current flows. We're just calculating the best conditions. And so as the current flows, obviously the concentration changes, like we looked at in the previous example, direction of electron flow is based on concentration. And then, of course, the standard potential, or the cell potential is going to change because of that change in concentration. So the cell will spontaneously discharge until it reaches equilibrium. Okay, so once Q is equal to K, then the reduction potential for the cell is 0. And this resembles something similar to a dead battery. There's no reason for electrons to flow anymore once equilibrium is reached, and so its potential will be 0. So at equilibrium, the components in the two cell compartments, the anode and the cathode, have the same free energy, and so the change in free energy is 0. And so this means that the cell no longer has any ability to do work because there's no reason for electrons to flow once we've reached equilibrium. Okay, so now let's use the Nernst equation to describe the cell. So the first thing that we need to do is get our balanced redox reaction. And so remember, all of these cell potentials are given in terms of reduction. And so we need an oxidation, so we're going to go with the smallest one. So we're going to flip our second one, our second reaction. So we have zinc as a solid going to zinc ions and 2 electrons. And then that makes the potential for this cell positive 0.76 volts. And then for our first equation, we need to multiply it by 2 so that we have equal electron transfer. And so we have 2VO2, 2 plus, 4 H plus ions, 2 electrons, and this going to 2VO and 2 H2O. And remember, just because we multiply the equation, that does not change the cell potential, and so it's still 1. So now if we add all these together, our electrons are going to transfer. We've got solid zinc, 2VO2, 4H plus, this is plus, that's aqueous, going to the zinc 2 plus ion, 2VO, and 2 water. And so our cell potential is 1.76 volts. Okay, so now we're going to use the Nernst equation to solve for the new cell potential. And so we know that the Nernst equation is E of the cell is equal to the standard potential of the cell, which is what we just solved for here, minus 0.0591 over N times the log of Q. And so we get 1.76 volts minus 0.0591 over N. N represents the transfer electrons. In this case, it's 2. Log of Q. And so Q is going to be products over reactants, but only the ones that are aqueous. We can't use liquids or solids. We could use gases or aqueous. So our products are going to be our zinc ion and our VO2 plus. So the zinc was 0.1 molar, and our VO2 plus, there's 2 of them, so we need to square it, and that's 0.01 molar, and we're going to square that. And that gets divided by our reactants. So our reactants, zinc solid's not going to work. Our VO2 and our 4H plus. So the VO2 concentration was 2, but there's a 2 in front, so we're going to square it. And then our H plus was 0.5, but there's a 4 in front, so we're going to do that to the 4th. And so if we solve for all of this, we get that our cell potential is 1.89 volts. And so it increased from the standard cell potential. And then one way to describe our cell is to do the line notation. And so we have our zinc anode, conductor, and then that's in zinc ions, and then we have our salt bridge. Now here, for our cathode, we have no solid conductor, so we would use platinum as our conductor, but then we've got VO, aqueous, we've got H plus, and we've got VO2, and then our platinum. Okay, so we can also use this in the opposite direction. We can use the cell potential to determine the concentration of an ion, and this works for pH meters. pH meters measure the concentration using an observed potential, and there are 3 components to a pH meter. So number 1 is the standard electrode of known potential, and the second is a special glass electrode that changes potential depending on the concentration of H plus ions in the solution. And so that's how we determine the pH. So it has a reference solution of dilute HCl in contact with a thin glass membrane. And then that electric potential depends on the difference between the H plus and the reference solution and then the tested solution. And then we also have a potentiometer which measures the potential between the electrodes, so we can look at the difference. So ion selective electrodes are electrodes that are sensitive to concentration of a particular ion, and we can make glass electrodes sensitive to particular ions by changing the composition of the glass. And then we can also detect other ions if we use a different crystal that replaces the glass membrane. So we can select for different ions instead of just H+, like for a pH meter. Okay, so we can also calculate equilibrium constants for redox reactions because we've been talking about the relationship between concentration, cell potential, free energy, and then equilibrium. And so we can use cell potential and the change of free energy to calculate K. So for a cell at equilibrium, we know that Q is equal to K and the reduction potential of the cell is 0. Talked about this already with concentration cells. And so we can take that relationship and substituting it into the Nernst equation at 25 Celsius, we basically get that to find the equilibrium constant, or the equilibrium expression, or K, we can take the log of K is equal to N times the cell potential divided by our 0.0591. So let's look at an example of that. So for the oxidation reduction reaction, and I have it written here, it's broken it up into the half reactions for us. We want to balance it and calculate the cell potential and K. All right, first thing we gotta do is write the overall reaction. And so here we know that we need a reduction, or these are both in terms of reduction, we need an oxidation. So we're going to flip this one and multiply it by 2 so we have equal electron transfer. So we have 2 chromium ions going to 2 chromium 3 plus ions and 2 electrons. And this changes the cell potential to positive 0.5 volts. And then our other equation is basically the same. So S4O6 plus 2 electrons goes to 2 S2O3 2 minus, and this gives me a cell potential of 0.17. And so if I put those together, let's see, my electrons will cancel. I have 2 chromium 2 plus ions plus S4O6 ion. That's 2 minus. That goes to 2 chromium 3 plus ions and 2 S2O3 2 minus. And our cell potential is 0.67 volts. Okay, so now we're going to use that to calculate K. We know that the log of K is equal to N times our cell potential over 0.0591. So log of K will equal, we had 2 electrons, our potential was 0.67 volts over 0.0591, and so log of K is equal to 22.6, and so then that means that 10 to the 22.6 is equal to K, which is 4 times 10 to the 22nd. This is a very large K value, but this is pretty normal for galvanic cells. Okay, so this is the practice that you guys are going to try on your own, and we'll discuss this in class. Have a good day.